So this week we're going to do the stereochemistry topic, which looks at isomers. We're going to start by just doing a little recap of structural isomers, which is what you've been looking at since National 5. And then we're going to take the idea of isomerism a wee bit further. So first of all, I would like you to draw two isomers of a molecule which has the molecular formula C4H10O. There are four possible answers. If you can draw four, then great. But pause the video here and jot them down. So let's have a wee think about these molecules. The first one, probably the most obvious one, is butan 1O. Remember, when you are naming whether it's an alcohol or an alkene, you've got to state which carbon atom the functional group comes on. So this would be not just butanol, butan 1O. And then, nice and simple, the second isomer could be butan 2O because our hydroxyl group has changed position. Another option is where we have taken one of the carbon atoms and put it on a middle. So we have here methyl propan 1O. Because there are no other options for where that methyl group can be, so if you move that methyl group to one of the outside carbon atoms, it would then become butan. We don't need to number where the methyl group is, but if you did, it wouldn't be wrong. But so this would be methyl propan 1O, and then our other option is methyl propan 2O. So that is something that you should be able to do already. You should feel quite comfortable with that. Remember, looking for the longest carbon chain, and knowing that an isomer, or the definition of an isomer, as you know just now, is a molecule with the same molecular formula, so in this case C4H10O, but a different structural formula in that the atoms are arranged in a different way. So isomers occur when there is more than one way to arrange the atoms in a molecule. So if you think back to National 5, when you were looking at isomers, you would perhaps build a butane molecule. You would take a CH3 group off the end, and you would take a hydrogen off what is now the middle carbon atom, swapping them to give you methyl propane. That's a structural isomer. We have the same numbers of each type of atom, but they are arranged in a different way. But there are different types of isomers. Structural isomerism is what you have looked at since National 5. But this week, we're going to have a think about stereoisomerism, of which there are two types: geometric isomerism and optical isomerism. And we're going to look at both of these in quite a bit of detail. So just in summary about structural isomers, we know they have the same molecular formula, but the atoms within the molecule are arranged in a different way. So for example, there are only two possible structural isomers of a molecule with the formula C3H8O. We have propan 1O and we have propan 2O. Many compounds will only have structural isomers. They won't display any stereoisomerism at all. But we're going to look, anything we're going to look at from now on, we're going to concentrate on stereoisomers. Okay, so stereoisomers occur when the bonding in an atom is the same. So unlike structural isomers, when the arrangement of bonds is different, stereoisomers, it is the same, but we're thinking more about how the atoms are arranged in space, so the spatial arrangements. And we're going to think about, are they superimposable? So if you think what superimposable means, it means to put one image perfectly on top of another image, and it would look as if there's only one there. Stereoisomers are non-superimposable. You cannot do that. So if you think about your hands, if you hold your hands out in front of you, no matter what way you arrange your hands, you cannot have them facing the same way and put one on top of the other perfectly. It doesn't work. Your hands you could class as stereoisomers. They are non-superimposable. And there are two types that we're going to look at. We're going to look at geometric stereoisomers and optical stereoisomers. So normally when we'd be looking at stereoisomers, we would do so using the mods. So when I see you on Thursday, we're going to spend a bit of time doing this. But in absence of that right now, we'll just try our best to talk through it. So beginning with geometric isomers. Geometric isomers only occur when you have a molecule that cannot rotate around certain bonds. Okay, so basically it must contain either a multiple carbon-to-carbon bond, like a double bond, or like a cyclic compound with, like, say, a cyclopropane, something like that. If you think about the mods, if you build a molecule of ethane, that single bond between the two carbon atoms rotates. You can rotate those carbons around, and that is what happens in reality. The bonds are always rotating. As soon as you turn that single bond into a double bond, you cannot rotate it. The molecule cannot move in the same way. The presence of that pi bond restricts the movement so that the molecule can't rotate. And there are two types of geometric isomers based on this. You have a cis isomer, which means the same, and you have a trans isomer, which means opposite. So let's have a look at some examples. In order for there to be a geometric isomer, and this bit's really important when it comes to identifying geometric isomers, we need to have a double bond, a triple bond, or a cyclic compound. But we also, on either side of the double bond, the atoms attached to the carbon within that double bond, the substituents need to be different. Okay, so there has to be two different groups. So for example, if we look at this carbon atom, we have one hydrogen and one methyl group attached to it. If we look at this carbon atom, we have one hydrogen and one methyl group attached to it. If we had a hydrogen here and a hydrogen here, that is not a geometric isomer. The two groups attached must be different, and you have to have that on both carbon atoms. Now, if you look at these compounds, they're butene. So they're both butene because we have 1, 2, 3, 4 carbon atoms with the double bond on the second carbon atom. If we look at where the substituents are, you have one here and one here. They are both on the same side. So this would be cis-butene. If we look at our other isomer, we have a methyl group here and a methyl group here. They are on opposite sides of the double bond. So we'd call this trans-butene. And the reason that's different is because of that double bond. That molecule cannot rotate so that both those substituents are on the same side. If that was a molecule of butane, it could do that. But the presence of the double bond means that that is restricted. So it cannot rotate. So we have cis-butene and trans-butene. And just a note to make you aware, this is propane. This is not a geometric isomer because on this carbon, the substituents are the same. And as soon as that is the case, it is not a geometric isomer. So please be careful of that. So when I see you on Thursday, I'm going to get you to build these models to hopefully make this a bit all a wee bit clearer to you. But if we look at these examples, we just want to identify what the cis isomer is and where the trans isomer is. So here is our cyclic compound. The isomerism is not going to involve this carbon here because we have two hydrogens attached to it. But this carbon and this carbon each have two different substituents and they are bonded together in a cyclic compound. So we have a chlorine here, a hydrogen here, a hydrogen here. The same substituents are on the same side. So this is going to be the cis isomer. And here, if you look, we have chlorine here. They are on opposite sides from each other. So that will be the trans isomer. Our next example, we have a carbon-to-carbon double bond this time. And there we have a carboxyl group. They're on opposite sides of this molecule. So that will be trans. And they're on the same side of this molecule. So this will be the cis isomer. So geometric isomerism can have a direct effect on both the physical and chemical properties of compounds. So have a look at this table. I've given you two different examples of geometric isomers. We have butyrene and dichloroethene. And I've given you their melting points and their boiling points. If you have a look, if you compare the melting points first of all, the melting points of the cis isomers are lower in both cases. But if you look at the boiling points, the melting points of the boiling points even of the trans isomers is lower. Now that seems a bit odd, and hopefully the next few slides will explain that to you. So let's first think about melting points. What is actually happening when we melt a solid? Think about how molecules or atoms in a solid are arranged. They're closely packed together, held together by intermolecular forces. And when you melt a solid, it is these intermolecular forces that you are breaking. Some intermolecular forces require more energy to break than others, so we'll have a higher melting point. And in some compounds, there will be more intermolecular forces depending on how the molecules can arrange themselves. And the more intermolecular forces there are, the more energy is required to overcome them. So let's have a look, first of all, at our cis isomer. Here we have our two methyl groups on the same side of the molecule. Now these methyl groups are quite bulky compared to the hydrogen atoms that are here. So when it comes to close packing, the close packing of these molecules can only really happen at this side of the molecule. So if I had another butene coming in here, it can only really pack in there as opposed to the bottom half of the molecule. There's not enough space for that to happen here. Compare that to the trans isomer, where you have a methyl group on each side of the molecule. The close packing can happen at either side. Okay, so we have our hydrogen here, our CH3. That can happen here as well. So because there's much tighter packing of the molecules, we can form more intermolecular forces when there's a trans isomer compared to when there is a cis isomer. And because it's easier to close pack, because there are more van der Waals forces, the melting point is higher. So there's a bit more ambiguity behind why the boiling points seem to show the opposite trend to the melting points. And it seems to be due to differences in polarity between the cis and trans isomers. So if you have a look at the cis isomer, if you have a look at the lines of symmetry, the cis isomer is more likely to be asymmetrical. Okay, so if we just write that in. And we know that in a polar molecule, any symmetry will cancel out polarity. But this is asymmetrical, so that wouldn't be the case here. This would be a polar molecule. But if we look at the trans isomer, again, this is easier to visualise when we have the models, but we'll have a look at that when we're in school. This is a symmetrical molecule, and you're more likely to have a symmetrical molecule when you have a trans isomer. The polarities cancel each other out. We learned that in higher. So overall, this molecule will be non-polar. So the consequence of that is that the forces holding those molecules together are weaker. Meaning that your boiling point is lower. Okay, so a little summary of what we've just looked at regarding melting and boiling points of cis and trans isomers. The melting point seems to be determined by shape because the molecules are pulled in to a highly ordered structure. But in terms of boiling points, it seems to come down to polarity. And the difference between asymmetrical and symmetrical molecules. So let's have a wee think about chemical properties. I've got quite a wee bit I want to annotate onto the slide here, so just bear with me. Geometric isomerism can have an effect on chemical properties, and we've got an example here. I thought it was best to highlight this as an example. So cisplatin, this the cis isomer on the left hand side here, that is a chemotherapy medication. A very effective chemotherapy medication. It's used to treat a lot of different types of cancers, but has horrendous side effects, especially sickness. And so while it has horrendous side effects, it can cause extreme sickness. Studies have shown, however, that the transplatin isomer is actually clinically ineffective against cancer cells. So even though it is almost the same molecule, that geometric isomerism, which is the only difference between these two isomers, it won't have any effect on it. I've put a wee link at the bottom of the slide here if you wanted to go and read a wee bit more about that. But cisplatin, really effective chemotherapy medication, can treat a whole variety of cancers, but the transplatin isomer has no effect against cancer cells whatsoever. So I thought before we moved on to look at optical isomers, I would go through a question about geometric isomers. you might find this useful when you're working through the revision questions once you've worked through this video. So there are 4 unsaturated isomers of butene. So that word unsaturated is important because that means it won't include cyclic compounds, because cyclic compounds are saturated. It's all single bonds. So there's 4 unsaturated isomers of butene. 3 of those are structural isomers of each other, and 2 are geometric isomers. And I'll explain why that 2 and 3 doesn't equal 4 in a wee second if that's confusing you. Right, so nice and simple. Let's just start with the structural isomers. So we're going to have, I'm just going to draw it out like this for the case of structural isomers. We have butanene. I suspect you can all do this. Just have an H in there. We have butene. And we have methyl propene, all structural isomers. So let's look at which one of these may have a geometric isomer. Now, we need to concentrate on the double bond here, okay? Here we have our 2 carbons in the double bond. If we look at butanene, this carbon has 2 hydrogens, this carbon has a hydrogen, and then this, let's class it as an ethyl group. Because this carbon has 2 hydrogens, there will not be a geometric isomer. Let's go down to the bottom one. This is in the same position. No geometric isomer. But this one probably does. So let's have a think. The best way to identify types of geometric isomer is to centre the hole drawn around the double bond. So let's draw our double bond first. Okay, so here we have carbon to carbon double bond. This carbon has a hydrogen attached to it, and the other bond is going to a methyl group. And if we look here, we have a hydrogen, and we also have a methyl group. Okay, so we have 2 methyls down here, 2 hydrogens up here. Each carbon in the double bond has different substituents. So this will be cis but 2-ene. Another possible way of drawing that, if we still centre it around there, is to have one side the same and another like this, where we have our substituents on the opposite side. So this would be our trans but 2-ene. Okay, so there we have, although we have drawn 5 structures, there is 4 isomers. We have 1 here, 2 here, and this one can either be cis or trans. So our second type of stereoisomer is an optical isomer, and the relationship between optical isomers is very much like the relationship between your 2 hands. So if we think about your 2 hands, your fingers are arranged in the same order on each hand. So we go from your thumb to your pointing finger, to your middle finger, to your ring finger, to your pinky. The order in which they are arranged is exactly the same, except They are a mirror image of each other. So no matter what way you hold around your hands, it is a mirror image. And that is what we're looking for in optical isomers. You think about your hand, a right-handed glove does not fit onto the left hand. It is said to be chiral, and this word chiral is quite important. It comes from the Greek word for hand, which is why we're going to reference our hands quite a lot. And optical isomers only exist when there is something called a chiral center. And we're going to look at what a chiral center is in the next couple of slides. So think about your hands again. If you compare your hands, if you look at one hand, there is no line of symmetry. So your hands are not superimposable. A chiral atom or a chiral carbon, that's what we're looking at here. We're looking to identify chiral carbon centers. A bit like your hands, where each finger attached to your palm is slightly different, each atom attached to our carbon atom is different. So if we look at this example here, we have carbon in the middle, we have a tetrahedral shape, and we have a different substituent at the end of each bond. So there are 4 different substituents. That is called a chiral center, and you will need to practice getting used to identifying where chiral centers are. So optical isomers arise wherever a molecule contains a tetrahedral carbon atom. So it means it has 4 single bonds. Remember, when you introduce a double bond to a carbon atom, you're removing that tetrahedral shape. So it's got a tetrahedral carbon atom that is a chiral center. So let's look at this molecule here. We have substituents W, X, Y, and Z. And let's say that is our right hand. Looking at a mirror image of this, I'm not going to bother trying to draw a hand, nobody wants to see that, but we can draw an exact mirror image of our molecule. So here we have Z, we have Y, and we have X. This is the optical isomer, and both of these molecules will exist. So where you have a chiral center, where you have an optical isomer, each molecule is known as an enantiomer of the other. It comes from the Greek word enantio, which means opposite. So it means you cannot exactly superimpose the structure because of the difference in the substituent groups. These are enantiomers of each other, much like your hands are enantiomers of each other. And there are ways of classifying these enantiomers. We can classify them as an R isomer or an S isomer. So, and as I said, enantiomers can be labelled as either R or S. And we need to be able to figure out which enantiomer is which. And we do that by looking at the substituent groups on the chiral center. And we have to look at the atomic mass of the carbon of the atom that the carbon is directly bonded to. So if we look here, we have carbon bonded directly to oxygen, hydrogen, carbon, and carbon. The atom there with the highest atomic mass is oxygen. So we're going to label this 1. And then we have 2 carbons. When it's directly bonded to 2 of the same, we go to the next one. So we're then oxygen versus hydrogen. So this is going to come first. So we're going to label it 2, 3, and 4. We then need to look about what direction that numbering is going. Here, it is going in a clockwise direction, so it's said to be the R isomer. If we look at the opposite, we'll number it the same. 1, 2, 3, 4. We follow that numbering in an anti-clockwise direction, so that is the S isomer. So here we have two enantiomers. Let's try and figure out which one is R and which one is S. So if we start with the one on the left hand side, we have substituents bromine, hydrogen, fluorine and chlorine. Bromine has the highest atomic mass, followed by chlorine, followed by fluorine and hydrogen. So if we follow this numbering round, we are following it in an anti-clockwise direction. So this will be the S isomer. We do the same here just to confirm it. We have 1, 2, 3, 4. Follow the numbering round. We're going in a clockwise direction. So this is the R enantiomer. So let's have a wee think about the physical properties of optical isomers. They have identical physical properties, more or less. I want to highlight physical properties because we'll come on to chemical properties in a minute. The only difference in physical properties is the effect that each enantiomer has on polarised light. We call enantiomers optically active. So if we have a wee look at what we mean, here we have a light source. And here we have a polarizer which produces plain polarised light. And by plain polarised light, we mean light that only travels in one direction. Okay, so if we have a look at our light source, the light vibrating in all directions, it goes through our polarizer, and then we only have the light vibrating in one plane, so just in one direction. When we pass that plain polarised light through a sample of our enantiomer, let's call this enantiomer R, it will rotate the light. So it may, this sample of R may rotate it by a degree of 50 degrees positive or to the right. Okay. The opposite enantiomer, so the R enantiomer, will have the opposite effect. So that rather than rotating that plain polarised light plus 50, it will rotate it in the opposite direction by 50 degrees. So they're said to be optically active. So we know that we can get the R enantiomer and the S enantiomer. We know that they have opposite effects on plain polarised light. But quite often, the R and S enantiomers will be mixed in equal amounts, so exactly 50% of each. That negates the optical activity, so the rotational effect then becomes zero. This is known as a racemic mixture. So when you have 50% of your R and 50% of your S, that optical activity is cancelled out. As you're working through the revision questions, there is quite a few that involve this idea of a racemic mixture, so just be aware of that. So a wee bit about the chemical properties of optical isomers. When enantiomers are reacting in a symmetrical environment, so with a symmetrical molecule that doesn't contain any chiral centres, both the R and the S isomer will react exactly the same way. But when they're carried out in an asymmetric environment, so involving a chiral molecule, they will react differently. So the kind of best example of this is to look at it in the context of a biological system. So say the human body, and say you're taking some sort of medication, so a drug of some sort. Biological systems involve the reactions of amino acids or proteins, most of which are chiral. They contain a chiral center. So the R enantiomer will behave differently in the human body than the S enantiomer. And as you can imagine, that has huge implications for drug design. And the biggest example, most infamous, unfortunately, example of this is the use of thalidomide. So back in the 50s, thalidomide began to be prescribed to pregnant women as an anti-sickness drug, which was a huge thing for women, especially back then, where they were quite often left, they would be at home with kids, and if they were suffering from any sort of sickness, let alone quite debilitating morning sickness, to be offered this drug which could take this away was a huge thing. And the rollout of thalidomide, it all happened very quickly, and women were taking it, quite commonly. However, the R thalidomide behaved as a sleep-inducing drug, and that was used as an anti-sickness. It was the R enantiomer that displayed the properties that we could use as an anti-sickness drug. Bear in mind this was used in pregnant women, and the S enantiomer, unfortunately, was a teratogenic and unfortunately led to quite severe, in some cases, birth defects. It might be to do with formation of limbs, or formation of vital organs, and unfortunately a lot of babies died not long after they were born. Now, this drug was sold as a mixture of both the R and the S enantiomers. So while the presence of the R enantiomer provided that anti-sickness relief for women, the S enantiomer at the same time was causing quite severe birth defects in babies that were born. That happened because a biological system displays chiral environments. Amino acids, proteins that are all involved in biological processes contain chiral centers, and therefore caused the difference in chemical properties to be displayed. So I thought I would finish by just going over how to identify whether a molecule has a chiral center or not. So here we have pentantool. So we want to start by looking at where that possible chiral center may be. So this carbon has 3 hydrogens, not going to be there. This has 2, 2 and 3, it's not going to be any of them. So it's probably going to involve this carbon here. And in order to identify that, I would draw this carbon showing its tetrahedral shape. So let's draw the carbon. Okay, we've got one bond coming up here with a hydrogen atom. The next bond is to CH3. The next bond is to a hydroxyl group. And the next bond goes to a C3 H7 group. So pentanol does have a chiral centre. So we can draw both enantiomers here. So let's have a go. Draw C3H7, our hydroxyl group down here, and our methyl group here. So let's identify which is which. So we have a hydrogen, a carbon, an oxygen, and a carbon. So this is going to be number 1. We have carbon to 3 hydrogens, then a carbon to a carbon. So hydrogen versus carbon, this is going to be 2. This will be 3. We would probably just ignore that and we'll look at the general trend as we go round. So as we move from here to here to here, we are going in an anti-clockwise direction. So this enantiomer is going to be S-pentanol. And if we just confirm that over here, we have 1, 2, 3, we could label that as 4, but the general trend in order to take in all of those numbers is going in a clockwise direction. So this would be our R enantiomer, so R-pentanol.